An understanding about the interior of the earth is essential for the geographers, since the endogenetic processes like earthquakes and volcanoes bring about changes on the surface of the earth. The relief on the earth's surface largely depends on the nature, processes and magnitude of the endogenetic forces which originate from within the earth. A proper understanding of the configuration of the earth's surface needs an understanding of the interior of the earth. The surface of the earth is largely a product of the processes operating in the interior of the earth. Exogenetic and endogenetic processes are constantly shaping the landscape. To understand why the earth shakes or how tsunamis wave is caused, why continents are drifting, why volcanoes erupt, what is isostatic adjustment, etc. The main aims of this lesson are: how do we know about the interior of the earth? The surface of the earth is solid, then what constitutes the interior of the earth? The interior of the earth and its composition has always remained a matter of great speculation among the geologists and geophysicists. It is difficult to have a complete and accurate knowledge of the composition of Earth's interior because it is beyond the range of direct observation by man and instrumentation. Most of our knowledge about the interior of the Earth is largely based on estimates and inferences. The sources which explain what constitutes the interior of the earth can be classified into two major sources as direct sources and indirect sources. Direct sources. The direct sources which can throw light on the interior of the earth are mining and drilling and volcanism. One of the direct sources which can throw some light on the composition of the interior of the earth is related to mining and drilling. The most easily available solid earth material, gold mines in South Africa, are as deep as 3 to 4 kilometers. Going beyond this depth is not possible as it is very hot beyond the earth. Besides, scientists have taken up number of projects to penetrate deeper depths to explore conditions in the crustal portions. Scientists all over the world are working on two major projects such as Deep Ocean Drilling Project and Integrated Ocean Drilling Project. The deepest drill at Kola in the Arctic Ocean has so far reached a depth of 12 kilometers. These projects and many deep drilling projects have provided large volume of information through the analysis of materials collected at different depths. Another direct source of information about the interior of the earth is in the form of volcanic eruption. As and when the molten material, that is magma, is thrown into the surface of the earth during volcanic eruption, it becomes available for the laboratory analysis. During volcanic eruption, hot liquid lava spreads on the earth's surface. Based on the observation, some of the scientists are of the opinion that there is at least one such layer below the earth's surface which is in liquid state. The source region of hot liquid lava or molten layer is termed as magma chamber, which supplies magma and lava during the volcanic eruption. It is inferred based on the volcanic eruption that some parts of the interior of the earth should be in liquid or molten state. But the inference, if refuted, if one considers increasing pressure with increasing depth inside the earth, increasing pressure increases the melting point of the rocks. Thus, inner part of the earth may not be in molten state. In spite of very high temperature prevailing therein, because the enormous weight and the pressure of the overlying material per incumbent load increases the melting point of the rocks. Therefore, the core of the earth should be in solid state. One pertinent question which arises here is what from where hot and liquid lava comes during the volcanic eruption. It is pointed out that when the pressure of the superincumbent load is released due to fracturing and faulting in the crustal surface, the melting point of the underlying rock is lowered, and thus rocks instantaneously melted because the required degree of high temperature is already present there. It is thus seen that no authentic information about the composition of the interior of the earth is obtained from the evidences of volcanic eruption. Indirect sources that can provide some clue about the interior of the earth includes temperature, density, pressure, theories related to the origin of the earth, seismology. Analysis of the properties of matter indirectly provides information about the interior of the earth. These properties are related to the temperature, density, pressure, etc. It is evident from the basis of information available from the findings of boreholes and deep mining that temperature increases from the surface downwards at the rate of 1 degree centigrade every 32 meters. At this rate, the temperature at the depth of 48 kilometers or 30 miles in asthenosphere would be between 1200 to 2000 degrees centigrade. The temperature of the center of the world should be more than 4000 degrees centigrade. The rocks and the minerals cannot remain in solid state at such a high temperature. It is therefore inferred that the source of lava eruption of volcanoes is at a depth of about 48 kilometers. Based on the research of scientists like Arthur Holmes, Van der Gracht, Conrad, etc., it may be noted that temperature increase with depth is not uniform. It varies depending on the presence of concentration of radioactive minerals in the interior of the earth and also the chemical composition of the rocks at various depths. It has been also concluded by the scientists that the rate of the release of temperature inside the earth undergoes sharp decrease at greater depths from the surface in the upper layers of the earth. An important source of the heat is radioactive minerals like uranium and thorium. These minerals are more abundant up to a depth of 100 kilometers, below which they are found much less quantities. It is thus appears that the rate of increase in temperature decreases downward with the depth. The thermal condition and temperature gradient of the interior of the earth, the temperature is around 1100 degrees centigrade at a depth of 100 kilometers, which is nearer to initial melting point. Thus, asthenosphere is partially molten condition. The temperature at the depth of 400 kilometer and 700 kilometers has been estimated to be 1500 degrees centigrade and 1900 degrees centigrade. The temperature at the junction of mantle and outer molten core standing at the depth of 2900 kilometers is about 3700 degrees centigrade. Density is defined as mass per unit area. Density can be calculated in cubic centimeters. The average density of the whole earth is about 5.5. The surface layer of the continents has a density of about 2.7. From these facts, it may be inferred that the density of the material of the core of the earth is much more than the density of the rocks found in the uppermost layer. The density of the intermediate layer is about 4.3. Thus, it appears that the density of the core of the earth is around 11.0. The density of the core of the earth is highest of all the parts of the earth. Some of the scholars think that high density of rocks in the interior of the earth may be due to excessive pressure on them. The geologists are of the opinion that the earth is composed of shells or layers, the density of which goes on increasing with depth. Numerous inferences can be drawn about the constitution about the interior of the earth on the basis of density of rocks, pressure of the weight of the overlying rocks, etc. It is believed that the outer layer, which is thinner part of the earth, is composed of sedimentary rocks. The density ranges between 2.7 to 2.9. Just below the sedimentary layer, there is another layer of the crystalline rocks, the density of which ranges between 3.0 to 3.5 at different places. The average density of earth is 5.5 cubic centimeter. Thus, it appears that the density of innermost layer or the core of the earth will be more than 5.5. The density of different layers of the interior of the earth is as follows. The density of different layers of the interior of the earth is as follows. If you take the outermost layer, that is the crust, the density is 2.5 to 2.9. Mantle or the intermediate layer has a density of 2.9 to 4.7. The outer core has a density of 11 to 12. The inner core has a density of 17. The average density of the earth is 5.5. The pressure exerted by the weight of the atmosphere inside the earth has also been used to determine the composition and structure of the earth. 1 atmospheric unit equals to a pressure of about 14.7 pounds per square inch. At this rate, at a depth of 2500 kilometers, the pressure is about 1 million atmospheres, and in the center of the earth, the pressure is estimated to be about 3.5 million atmosphere. Such a high pressure in the interior of the earth exercises a powerful influence on the temperature and the physical state. There is a direct proportional relationship between density and pressure. That is, density increases as the pressure increases. Very high density of the core of the earth is due to very high pressure prevailing there because of the superincumbent load, that is the weight of the overlying rocks. The scientists revealed that the core of the earth is made from iron and nickel. Evidences from the theories of the origin of the earth. Various theories were put forth regarding the origin of the earth. These theories assume that the original form of the earth to be solid, liquid or gaseous form. According to planetesimal hypothesis, the earth is originated due to the accretion or aggregation of the solid dust particles known as planetesimals. Based on this, the core of the earth should be in the solid state. According to tidal hypothesis, the core of the earth should be in liquid state because the earth has been taken to have been formed from the tidal material ejected from the primitive sun. According to nebular hypothesis of Laplace, the core of the earth should be in liquid state. In 1755, Laplace considered earth as a part of the sun. From this point of view, the earth was a mass of hot gases. The upper part of the earth cooled slowly into solid form. It was therefore thought that the interior part of the earth must be in a form of liquids and gases. There may be only two possibilities, namely, either the core may be in solid state or liquid state. The behavior of the seismic waves in the different layers of the earth provides most authentic evidence about the composition and the structure of the interior of the earth. The study of seismic waves provides complete picture of the layered structure of the interior of the earth. Seismology, which is a science related to earthquakes, is the major source which provides an authenticated information about the natures of Earth's interior. Seismic waves have two properties which make them particularly useful in revealing the Earth's internal structure. One, the earthquake waves are reflected when they strike the interface between material having different elastic properties and density, according to Snell's law. Secondly, the seismic waves tend to bend or refract towards the regions where they go more slowly. This is not the unique property, rather it is shared by all the waves. When a wave strikes the interface between two materials, the amount by which it is bent depends on the differences in the wave velocities between two materials. When the wave speed changes gradually within a material, the wave will also bend gradually. The more gradual change in the wave speed, the more gradually the wave will bend. Consequently, when the seismic wave crosses an interface between two distinct regions, the change will abrupt, and when it passes through the regions where there are gradual changes in the pressure, temperature or composition, the waves will bend gradually. The direction also changes as they reflect or refract when they are coming across the material with different densities. The seismic waves are also divided into three broad categories: primary waves, secondary waves and surface waves. Primary waves are also called as P waves or push waves, or compressional, dilational or longitudinal waves. They are of high frequency, short wavelengths. This type of waves, the motion of the energy particles is in the direction of the propagation of primary waves. Primary waves can pass through solid, liquid and gaseous material. They travel faster through higher density rocks, and in liquid media their velocity decreases. Their velocity may range between 8 to 13 kilometers per second depending upon the material through they travel. P waves are similar to sound waves. P waves move faster and are the first one to arrive the surface. Secondary waves or the S waves are also called as transverse or distortional or shear waves. They are called secondary waves because these waves arrived after the P waves. In these waves, the motion of the energy particles is at right angles to the direction of the wave propagation. The secondary wave can also pass through solid media. These waves cannot pass through the liquid material because S waves cannot travel through the liquid material. They do not pass through the core of the earth. The velocity of these waves depends on the density or rigidity of the material. The path of the P and S waves, through which the interior of the earth is concave due to the increasing velocity with increasing depth. The velocity of these waves changes as they travel through material with different densities. Surface waves are also called as L waves. These waves are observed only in the surface of the earth and therefore called as surface waves. They are confined to the outer part of the crust and their path is convex in nature. They cover the longest distance of all seismic waves and are recorded last on the seismograph. These waves are most destructive in nature. If the earth would have been composed of homogeneous solid material, the seismic waves should have reached the core of the earth in a straight path. Instead, these seismic waves adopt a curved and refracted path. An understanding of the interior of the earth is provided by both direct and indirect sources. The direct sources are evidences is mining, drilling and volcanic activity. These direct sources have not provided any complete understanding of the interior of the earth. The mining activity could provide information up to few kilometers only, whereas volcanic activity could tell us that some of the interior of the earth is in liquid state. The indirect sources of the information are related to temperature, density, pressure and seismology. The rate of temperature increase inside the earth undergoes sharp decrease at greater depth from the surface. The temperature decrease up to a depth of 100 kilometers is around 1100 degrees centigrade, whereas it is around 4300 at the depth of 5100 kilometer.